Welcome to This Explainer. Today, we're diving into something that sounds intensely mathematical, but is actually a deeply physical, incredibly logical system for navigating the universe around us. We're talking about vectors. A lot of times vectors get introduced as just these abstract little arrows drawn on a chalkboard, but we're going to look at them totally differently today. We're treating vectors as the ultimate tools for navigating physical space, plotting positions, and charting a course between the stars. It's a fascinating system, and by the end of this explainer, you're going to see exactly how it all connects. All right, let's lock in our baseline vocabulary. You've probably heard these terms before, but let's make sure we're on the same page. A scalar is just an amount, like your speed or the temperature outside. But a vector? Man, a vector has ambition. It requires two distinct pieces of information to be fully understood. It absolutely must have magnitude, which you can just think of as length or distance, and it must have direction. You aren't just moving fast, you're moving fast due north. That one distinction changes everything. It's literally the foundation for everything from 3D computer graphics to how your phone's GPS actually works.
Here's the roadmap for our explainer today. We're going to cover pinning down positions, getting from point A to point B, the core vector relationship, and finally scaling and direction. Let's jump in.
Part 1. Pinning down positions, starting with the origin point.
Imagine you're standing right at the absolute center of the universe. That's you at our origin point O. Now look up at the night sky at two distant stars, A and B. Think about drawing invisible lines directly from where you're standing right out to those points. Those lines? Those are your position vectors, A and B. They completely pin down exactly where each star sits relative to you. They tether those stars to your exact perspective, and you don't even need any arbitrary grid lines or a massive universal map to do it.
Moving right along to part 2, getting from A to B and plotting the jump.
So, we know exactly where our stars are anchored, but the real question is, what does it actually take to get from one to another? We know where A is, we know where B is, now we just have to plot the jump.
To figure out the vector from A to B, which we just refer to as vector AB, we need to calculate our displacement. Think of this as your ship's exact heading and distance rolled into one. The math here is beautifully straightforward. You just subtract your starting coordinates from your destination, that gives you your X and Y travel components. And to find the actual raw length of that journey, you just run those components through the classic Pythagorean theorem. Honestly, it's just high school geometry powering interstellar travel.
When you map that calculation out in physical space, it's literally just a straight arrow. It starts right at our departure point, star A, and points straight to our destination, star B. And that arrowhead is incredibly important here. It explicitly shows our direction of travel. We aren't just hovering in the void between 2 points. We have a definitive starting line and a finish line.
Which leads us perfectly into part 3, the vector relationship and bridging the gap. See, we're juggling two separate perspectives now. First, there's the static view. Where are A and B relative to the origin? That's you standing on Earth looking through a telescope. Then there's the active view. How do you actually get to B from A? That's you in the pilot's seat making the journey. To really master vector logic, we have to bridge the gap between those two ideas.
And that brings us to the famous triangle law of vector addition. If you trace a path from the origin up to star A and then take a turn over to star B, well, the net result of that journey is exactly the same as if you just shot straight from the origin directly to star B. In math terms, vector A plus vector AB equals vector B. You might be taking different paths, but your destination is mathematically identical.
And here is where it gets really cool. If you just rearrange that triangle law, you unlock the absolute golden rule of navigation. If A plus AB equals B, we do a quick bit of algebra, subtract A, and boom, vector AB equals B minus A. The vector between any 2 points is simply the difference of their position vectors. If you want to find the exact path to your destination, you literally just take the destination's locator vector and subtract where you are right now. It is simple, elegant, and just perfectly logical.
All right, final section, part 4, scaling and direction, and how we modify the journey.
The beautiful thing is once you have a vector, you're not stuck with it. You can multiply a vector by a regular old scalar number to totally stretch, shrink, or completely reverse your path. Multiply by 2, you go twice as far. Multiply by 0.5, you cut the trip in half. But check this out. If you multiply by a negative number, the length stays exactly the same, but the vector flips 180 degrees. You've essentially thrown the spaceship into reverse.
And the ultimate rule of scaling reveals itself pretty quickly when you look at it visually. No matter how you stretch it, shrink it, or flip it around, a scaled vector is always going to stay perfectly parallel to the original. They are permanently locked on that exact same geometric track.
Because of that parallel nature, math has a very strict definition for when two vectors are actually considered equal. It takes two things, and there are no exceptions here. Their magnitudes, their lengths, have to be perfectly equal, and they have to point in the exact same direction. Parallel but pointing opposite ways? Not equal. Pointing the same way but one is just an inch longer? Not equal. Equality demands a flawless match in both length and heading.
So we've got magnitude down, but what if we just want the heading, like the pure, distilled essence of direction with zero distance attached to it? That is where we use a unit vector. We write it as a v with a cute little hat over it. To get it, you take your vector and literally divide it by its own magnitude. You are basically stripping away the specific distance until the length is exactly 1. It becomes nothing but a pure directional pointer.
We've built a pretty incredible toolkit in this explainer today. We started with nothing but a fixed origin point and a blank sky full of stars. And from there, we figured out how to pin those stars down, plot displacements, understand the triangle law linking everything together, and finally how to scale our paths and isolate pure direction with unit vectors. This isn't just chalkboard math. This is the literal foundational language of physics, engineering, and navigation. So with this logical system now in your back pocket, if a unit vector gives you pure direction, where will your next vector take you? Thanks so much for joining me on this explainer. Keep learning, keep mapping the world around you, and I'll catch you next time.